Not surprising, we really take a change of direction now because we're really going into some really real statistics, hypothesis testing, and it's a bit different than the material that we were working with before. Right, so I did have some questions on assignment 4. Question 4, 5, and 6 came up for a couple of people, and particularly the last two questions. I think they're like 14 and 15 or 15 and 16. And I want to go over. Matter of fact, I think maybe it might even be worth going over the entire test quickly. Okay, I'm going to start with those questions because I want to make sure I get those done because people asked about them. But maybe we'll go back and we'll look at a bit more of these problems. Okay, so let me see if I can find it. Where is Facebook? Here we go. All right, folks. Okay, here we go. So I'm going to start the test here in this window and to continue. And I'll go straight to the ones that cause the most problems first. That's last couple of problems. Oh, really, 10, 11, and 12, actually. Okay. Now, the first 10, question 10, pretty much I really had a pretty good handle on. Probably an infant is born, an infant is born prematurely in Mexico is 0.15. What is the standard deviation for the proportion of premature births for repeated samples from this population size of size n equals 25? Right, and we know the formula for its standard error for a proportion is p times 1 minus p over n, and take square root of that. Okay, now what we're describing here, standard error or standard deviation for the proportion of premature births for repeated samples using from the population of size 25. So the sample size is 25. We're asking about the distribution of samples that what the proportion would be in the distribution of samples if you repeat it over and over again that size. Basically, central limit theorem, right? So most of you figured that out, that this is, let me see if I can't do this real quickly, that this is going to be, let's say, P, it's going to be equal to the standard, standard error, of equal to square root of 0.15 times 0.85 over the sample size, 25. Okay, let's actually work that out. And there we go. Okay, so let's clear this first. 0.15 times 0.85 equals this divided by 25 is going to be equal to 0.005. I'm going to find square root of that, which is 0.0714. I'm going to call it 0.071 for our purposes right now. 0.071. I went to 3 decimal places on this. You could have actually typed in 0.014 if you wanted to be a little bit more accurate, or if you wanted to avoid a rounding error and so on. Since this is the last step, I was perfectly willing to round it. In other words, we're not going to use this at this moment for further calculation. If we were, I would avoid rounding this. I would continue to keep as many digits as I would keep, at least one or two digits more than the significant digits. In other words, 2 significant digits. I would keep at least 3 significant digits here, like the 714, if I'm going to continue to do some calculations. So I'm going to go ahead and, or at least at the end, I would keep as many as I could. Otherwise, I really like using Excel for this, because if you use Excel, even if you have the cell set to only show 2 significant digits, it's actually buried in the cell. It actually stores the entire number. So I'm going to go ahead and go on to the next one. Okay, excuse me. So we would expect 95% of the proportions for a sample of size n equals 625 to be between this number, lower end of the confidence interval, and between this number, the upper end of the confidence interval. So, you're right. I think that's not very neatly worded. This question refers to the proportion in question 10. And what I was really driving at there was that if you took from that same population, where P is equal to 0.15, If you took repeated samples from this population of 0.15, that it's asking, instead of taking a sample size of 25, you took a sample size of 625, what would be the range of values that you would find 95% of the samples to occur in? So that would be, let's see, we expect we repeatedly took samples of 625. If this is 0.15, the our estimate of what the population proportion is, well, then I would expect 95% of the time for these values to be between two standard errors below the mean and two standard errors above the mean. In this case, the standard error is going to be equal to the square root of 0.15 times 0.85 over 625. Okay, I'm going to rephrase that problem. I'm a little reluctant to do it right now because I don't want it to affect previous answers that people have put in. But I'm going to rephrase that problem so it makes a little bit more sense, or it's a little bit clearer. But using the same proportion as before, really, it's a continuation of the same problem. Unfortunately, it's difficult to make Blackboard give you sequential numerical answers. So I have to break up the problem into a introduction of the problem and then subsequent answers based on that. So at any rate, let's give this a try. Well, clear. That's going to be 0.15 times 0.85 divided by, equals, divided by, let's see, divided by 625 is equal to 0.0002, and I'm going to take the square root of that, and that's equal to 0.014. So I'm going to use 0.014 at this stage. Again, if you're going to do subsequent calculations, it would be worthwhile preserving an extra couple of digits there. 0.014. Well, let's take a look at this. The standard error here is 0.077%. Over here, it's less than 2%, right? So if I were to look at a range of these values, right, I would look at P plus or minus 1.96 times the standard error. And this value here is the margin of error, how much I'm adding and subtracting from P to get a range of values, right? Lower confidence interval, upper confidence interval, or similarly, if we're looking at repeated samples, the lower limit that we would expect for our 95% of our results to be, and the upper limit that we would expect 95% of our results to be. So if I take this, had it been using a sample size of 25, this would have been approximately plus or minus 2 times 7%, plus or minus 14%. Well, in the case of a larger sample size, look how it shrinks that margin of error. Now it's going to be P plus or minus approximately 2 times 1.5%, plus or minus about 3%, right? So it's a really significant difference when we apply this to a much larger sample size. Okay, so at any rate, I don't. There's another issue with that small a sample size. In our case, not big an issue because you knew the population proportion. So I'm not gonna raise that issue now and confuse things further. But that's okay, right? So what is the answer to this going to be? Well, it's going to be 0.15 plus or minus 1.96 times 0.014. Hopefully I carried, I didn't do what I told you not to do, and I carried enough digits to not have a rounding error, but let's do it anyway. See what I got. Okay, it's going to be, let's see, 1.96 times 0.014 is equal to 2.7%. I'm going to clear my memory here. I'm going to add this. And I'm going to clear this. So I'm going to say 1.96 minus our margin of error, and that's equal to 1.93. Oh, excuse me. Actually, let me go back to that again. It's going to be 0.15 minus, recall our number here, minus that 2%. It's going to be 0.123. I'm going to call it 0.123, 0.0123. 0.0123. It's going to be the lower range, and the upper range is going to be 0.15 plus my margin of error, which is going to be 0.177. Okay, so basically, if I took repeated samples, if I know the population proportion is 15%, if I took repeated samples of size 625, I would expect that that those sample results will come back 95% of the time with a proportion for the sample between 0.0123 and 0.177, between about 12% and about 18%. Okay, so that's really what that was driving at. I'll try and reword that at some point once I lock in the everybody that's completed it and got everything got 100% on it. I'll lock it in. I'll go back and I'll change the wording of that. So next time we use it, that makes a little bit more sense. Okay, so let's take a look at the other problems that caused issues. And that was 4, 5, and 6. A couple of people asked that. Okay, so where did you start there? Let's start with question 1, as a matter of fact. Among adults in the U.S., the distribution of albumin levels is a type of protein is roughly symmetric, with a mean 29.5 and standard deviation of 9.25. Suppose that you select many repeated samples of size 20 from this population and calculate the mean for each sample. What would you expect the mean of the sample means to be? Well, since it's symmetric about the mean, and we know our rules about our confidence interval, we would figure that our mean for our repeated samples would approximate the mean for the population. So we'd say 29.5 there. Would you expect the standard deviation for the repeated? What would you expect to be the standard deviation for the repeated sample means? In other words, what's the variability of these repeated sample means of size 20? Now, keep in mind, we know sigma is 9.25, so we can justify doing this even with such a small sample. So we know that if we take repeated sample means, let me get a fresh sheet of paper here. Okay, whoops. Okay, and we know that our standard error for repeated samples, variability for repeated samples is equal to the standard deviation of the population, which we know to be 9.25 here, over the square root of the sample size, over the square root of 20. Yes, let's actually work that out. Clear that and clear that. And I'm going to take 9.25. First, I'm going to find the square root of 20. 20. Take square root of that. And I'm going to put it into memory. I just cleared the memory, so I can do that. And now I'm going to say, let's clear this, and I'm going to say 9.25 divided by the square root of 20. And that's equal to 2.07, I'll call it. Okay, so hopefully I got that right. So we can move on to the next part of this and get that right as well. Okay, let's see. Okay, standard deviation for this repeated sample means. In other words, it's called the standard. Another name for this standard deviation sample means is called the standard error, of course, right? You know that. What proportion of the means of samples of size 20 are expected to be larger than 33 milligrams per 100 ml? So I'm going to go back here, First, before I do that, I want to make sure I'm getting the right answer here. Let me go back a step. I'll let you take a look behind the curtains here, since most people have already completed this assignment. Okay, let me go back another one. Okay, let's go back here and make sure I got it right. Okay, and okay, yeah, we're going to emulate that. Standard error, 2.1. Is that what I got? Yep, about 2.1. Just so you can see, I put down 2.1 here, and you had an answer range of 0.1. So you could have 2 to 2.2, and it would have been an acceptable answer. Although that's the way I coded the answer. I really would rather prefer that you maintain at least 3 significant digits for something like this. Right? So don't be fooled by the range of answers. That's just so if you're off that tiny bit, that you're not penalized for it. And standard error. Okay, let's go to proportion of these samples that are larger than 33. Okay, now remember what we're talking about here is not the population anymore. We're talking about the distribution of the repeated samples of size 20. Well, we know from the previous answer that the average result from a sample of size 20 is going to be 9.25. Right now, we want to know, well, what percentage of the samples would we expect to be larger than 33? So 33 is going to be over here. Okay, and that seems weird. Oh, I'm sorry. Did I get that wrong? The mean is 29.5. Excuse me. 29.5. Isn't that funny? I did that unconsciously, I guess. 9.25 and 29.5. That's kind of odd, right? Yes, I liked those numbers that night. Okay. Whenever I put that together, I must have liked those numbers. Okay, 29.5, and happened to use the same digits, moved over one. So 33. What percentage of the means for the repeated samples are going to be larger than 33? We know that the central limit theorem tells us that repeated samples from a population are also going to form a normal distribution. Even if the original distribution isn't perfectly normal, they're going to form a normal distribution, and that the variability distribution is going to be the standard, what we call the standard error, or in other words, sigma over the square root of n, which we found to be 2.07. Okay, 2.1 if we rounded it. So I'm going to take this percentage here is what I'm interested in, greater than 33. So I need to use either my z table or Excel or some other method to find what the area to the left of 33 is. And then, since I'm interested in this area, I have to subtract it from 1. So I'm going to use Excel this time. A lot of advantages to using Excel because you can go back and check your answers, and you can look at the embedded formula and so on. And before you can do that, you have to find it. There we go. Okay. Okay, I don't need that. Oh, new workbook. And I'll make it a little easier to save. We don't need all these cells up here. Do that. Okay, so now there's two functions I could use, two ways I could do this. One way I could do this in Excel is I could use the function norm dist. I could use norm.dist also. A lot of times there's two versions of these because older versions of Excel use the function called norm dist, and newer versions of Excel they added a function. They added many other functions that had different assumptions or versions, and they put a dot in there to describe them. So you'll see this with a lot of other functions. In the case of norm dist and norm, the reason why they kept norm dist and they have norm.dis, they have two functions in there to do exactly the same thing, is because if people use that previous function in macros or programs that they wrote, they wanted to make sure that the old version worked, even though they went to a new version as well. But in this case, in the case of norm.dis, and norm.dis is exactly the same result. They wind up giving you exactly the same result. Doesn't matter which one you use. I got a parentheses. Parentheses, it automatically prompts me or helps me out. So first thing it wants is X, or the value you're interested in, which is 33. And then it wants the mean, which is 29.5. And then it wants the standard deviation. In our case, it's the standard error. The standard error was 2.07. And then it wants the value true or false. We almost always use true for this function because we're always looking for the area to the left of this value. False only gives you what kind of would be a value for that specific outcome of 33, but even then, it's that it represents almost a straight line, an arealess straight line. So it really doesn't make any sense to use false for this function. This function, always use true, and it comes out to be 0.9545. Again, nice thing about it is Excel is I can say equals 1 minus this value and get our answer of 0.045. The other way I could have done about 4.5%. The other way I could have done this is to actually calculate the value for z, the z-score for 33. And I'm going to do that here. Okay, so z is going to be equal to x minus the mean over the standard deviation, or standard error in this case, right? I'm going to put parentheses around there just so you remember that you got to resolve the top there before you divide. So I'm going to do that right here. So z is going to be equal to, I'll use the parentheses here, 33 minus 29.5 divided by 9.25. Oh, I'm sorry, was it 9.25? I think it was 9. No, it was 2.0. 2.07. Okay, so what does that come out to? That comes out to a z-score of 1.69, right? We just solved for the z-score. So now I got a z-score. I still got to find the area to the left of that. Well, there's another function in Excel called norm sdist. Norm sdist. Notice how it prompts you here and helps you out. Norm sdist. And notice all it wants in norm sdist is the z-score. So if I put the z-score in there, which was 1. Actually, I can just click in here. I can either type it in or I can just click in there and have it use that number. If I type that and hit enter, I get the same value as I got before, right? So you can use either one of those two functions, norm dist. And if I click in here, you'll see the function norm or norm.dist. And if I click in here, you'll see the function norm sdist, norm standard distribution. Okay, so you can use either one of those two. So let's take a look at the next part of this problem, which is number 5. What proportion of the sample mean is expected to be less than 28 milligrams? Oh, okay, good. Okay, we kind of have a head start on that, don't we? Okay, less than 28. Less than 28 would be the area from 28 down, right? So we got to either figure out the z-score, 28 minus 29.5 over the standard error. Remember, again, we're working with the sample distribution, so we're using the standard error instead of the standard deviation, the population, sigma. So we got to find that area in there, right? So I can either calculate the z-score, 28 minus 29.5 divided by 2.07, right, for the z-score, and convert that using the table, or I can go back and use Excel. Right? You can go to the table if you want. More than one way to skin a cat, right? Okay. So I like cats, so I take that with a grain of salt. So at any rate, let's see, equals, 28. I'll do it this way first, minus 29.5, parentheses, divided by 2.07. So the z value for that is minus 0.72. Notice minus because it's on the left side of the mean for the sample distribution. And if I want to find out what the value is, that's the z-score, I know what the area that represents is, I can say equals norm. Remember, norm S dist is the one that will convert the z-score into a area in this distribution. So I'm going to just click into that rather than retype it, and it gives me 0.234, okay, 23.4%, or 0.234 is going to be the area to the left of that. Okay, so the other way I could have done this is I could have gone to the tables. Okay, and first you would have calculated your z-score, right? That you could have done manually. You would have gotten the same thing I just did using Excel. It's just simply 28 minus 29.5 divided by 2.09 to get the z-score, and then you can go to your t-table. Oh, I'm sorry, z-table. I got ahead of us here. Here we go. And minus 7.24. Minus 0.7201, 0.00102 is 0.2358. And 0.2358, what did I get there before? Let me go back to 0.23. We're a little bit off, right? In that third significant digit, we're a little bit off, partly because when I use the table here, I got to 0.07. It was really between two and 3, right? Because that next digit was about almost halfway to the next level, right? It's really 20. The best I could do here was 0.72, right? And it really, our result was between 0.72 and 0.73. So the table was not quite as accurate as using Excel, which takes it well beyond just the three significant digits here, two or three significant digits here, 0.07012, and this would have been 0.073 would have been here. So the answer would have been between these two, really. And Excel gave us that answer. And this one, we took the one that was closer. But either one of these you would have enough of a range in your answers, acceptable answers, that either one of them would have given you the correct answer. Let's see if we got something else there. Okay. Yeah, in fact, you can see it here. Got 200ths of an either way. They would have been an acceptable answer. So 0.07 to 0.074 would have been marked correctly. I think the rest of these pretty much everybody got pretty well. Let's go. Might as well go finish them up. In Denver, Colorado, the distribution of daily measures of ambient acid gases is slightly skewed to the right with a mean of 1.16 micrograms per cubic meter of acid gases in the air, right? Probably, I don't know why Colorado would have so many acid gases. Maybe they have a lot of power plants out there, right? So let's assume I could have picked somewhere else, like Idaho or something like that, or somewhere where they have a lot of power plants or something. 0.161 micrograms per cubic meter is the average. The standard deviation is equal to 2.25. Now again, notice that we know the population standard deviation. We know the standard deviation of all the possible readings, right? That's kind of a little bit of a cheat, but we're going to use it for now. When we get on to assignment 5, we're going to be dealing in situations only where we don't know the population, where most of the time we don't know the population sigma. So we have to use the t-table or t-tests instead. So we'll be getting onto that. So based on central limit theorem, the distribution of sample means of size 100 is expected to be simply expected to be skewed to the right, skewed to the left, normal, or bimodal. Well, central limit theorem tells us that if you get a large sample size, and 100 is a pretty large sample size, right? You can start to debate large sample size once you get over about 30 or 35, but certainly at 100, you're getting a sample size where you could apply the central limit theorem. And the central limit theorem tells us that even though this is slightly skewed, the population values are slightly skewed to the right, the distribution of repeated samples of size 100, that one is going to be normally distributed, or normally enough distributed for you to use it effectively to make predictions. Okay, so we're going to say that's going to be normal. The standard deviation is sample mean. Standard error is expected to be, okay, what's the standard error going to be equal to for n equals 100? Well, that's going to be equal to 2.25 divided by that sigma, divided by the square root of the sample size, divided by 10. So that's going to move a decimal place over one place. That's going to be 0.225. That's pretty convenient, right? So the mean of the sample means is expected to be, well, the mean of the sample means is expected to be the same as the mean of the population, or 1.61. Okay, and then you got into the last part of it. We didn't ask you to do a confidence interval there. So I think we got through all of those. Okay, so hopefully that helps a bit.